So F is for force. It's a push or a pull on the object. It's measured in newtons, and we have to be careful because sometimes we'll have something say like a 10 Newton box or a 10 kilogram box, and those units tell us that it's either telling us about a force or the object's mass. Mass is the measure of stuff in the object. The symbol in the equation is an m, and the unit is kilograms, kg. Acceleration is the change in an object's velocity over time. And A is for acceleration, but also G is for acceleration because G is the acceleration caused by the force of gravity. And on the planet Earth, the acceleration caused by the force of gravity is 9.81 meters per second squared. Notice this is an acceleration and not a force. So the acceleration caused by gravity is not the same as the force of gravity pulling or pushing on an object. We do have one new one today, the coefficient of friction. That's a measure of how sticky a surface is. So when you push two things against each other, if they slide really smoothly, there's a small coefficient of friction. If they're really hard to slide against each other, that means the coefficient of friction is probably bigger. You'll hear me, this is a Greek letter, and the way you write it, it kind of looks like that when you write it. You start with the big swoop at the front, and it's called mu. So just like this is called sigma, and this is called delta, that's the name of the letter. This one is called mu. And mu doesn't, the coefficient of friction doesn't have any units. So that's nice. It doesn't have any units to worry about. Ready? Like I said, the new one is this one. The other three should be somewhere in your notes already. So keep in mind that weight is not the same as the object's mass. Weight is a force in this class. Weight is the force of gravity pulling on an object. So we know we're given a weight when it says like the unit, when it has the unit of newtons. We know something is a mass when it has the unit of kilograms. So an example would be a 50 Newton box. So if we're given the information of 50 Newton box, that means we have the force of gravity on that object. If we're told that we have a 50 kilogram box, that means we know the mass of the object. And you'll see the difference in the calculations in one of our examples today. Remember, you don't need to write this word for word. You can abbreviate, you can summarize. Okay. Now this does have, I know this one has a lot of words, but the most important words are really like here, here, and of course the highlighted equation. So force of friction, most of the time I'm not very picky about whether it's static friction or kinetic friction. Most of the time I'm just like, if friction is friction. You treat static friction and kinetic friction the same way. They both have the same equation, so it doesn't really matter which you're talking about. Static friction is when the object is motionless. So you can imagine this like you're pushing really, really hard against something really heavy and it's just not budging. That would be static friction. Kinetic friction is when you already have the object moving. So you overcame the static friction and you got it moving, and now it's just sliding. That's kinetic friction. So static means staying still, kinetic means moving. So static friction is when the object's motionless, and kinetic friction is when the object is sliding. Static friction is always greater than kinetic friction. And you've also probably felt this before if you had to move a very heavy, like a couch or a table. It's more difficult to get the couch moving than it is to keep it moving. Once it's moving, it's a little bit easier. And then down here it says that the coefficient of friction is never bigger than 1. So that's both of these here, that static friction is always bigger than kinetic friction, and that mu is never bigger than 1. Both of those are important for calculations. This one could also be important for concepts, right? Like which takes more force, like pushing, making a boulder start moving or making a boulder keep moving with friction. It would be, start moving would be more force. This is important for calculations, right? It's one way to check yourself if you're asked to find the coefficient of friction. If you get a coefficient of friction that's bigger than 1, then you know somewhere in your problem you've made a mistake. And then in our highlighted equation, we have the force of friction equals the coefficient of friction times the normal force. So friction can only happen when an object is on a surface. So it makes sense it's also going to relate to the normal force pushing up on that object. Right? Ready to see an example? Okay. So I kind of, for today, I just want to focus, there's a couple that have like a part A and a part B. And I just kind of want to focus on doing the first one together and leaving the second one for you to do on your own later. And I will have, like, I'll probably go in and edit the video and be like, the answer to this one is this, if you work it out on your own. All right? So, first one. A museum curator moves artifacts into place on many different display surfaces. Find the force of kinetic friction in the following situations. Sliding a 145 kilogram aluminum sculpture along a horizontal steel platform. So we have mu, the coefficient of friction is 0.47 for the aluminum sculpture and the steel platform. When I see this problem as a physics teacher and as somebody who's done a lot of physics problems and force problems, I see we're finding the force of friction and we're given a coefficient of friction. So already in the back of my mind, I know that we're going to have to use the equation that has the coefficient of friction in it. So the coefficient of friction only shows up in one spot. It's in that equation. So in the back of my mind, anytime I see coefficient of friction, I know I'm going to have to use that equation. But before we get to that equation, let's still do our 3 steps. So what are our 3 steps? First step, do what? Free body diagram, right? So in this case, what forces do we have on our object? Force of gravity. What else? Normal force, right? It does talk about surfaces. And because the floor is horizontal, right? It's a horizontal steel plate or horizontal steel platform. Remember, normal means perpendicular to the surface. So that means the normal force is straight up. What else do we have? Force of friction. If it's asking us to find the force of friction, then there's, yes, probably some friction going on. And there's probably also, we're probably having to push it, right? So probably some applied force. What's our second step? Summation equations. Are we going to have one long summation equation with all 4 forces on it? Why not? Yeah, we've got to keep the components kind of separate from each other. If we're going to add things and subtract things, we want them all in the same direction, right? Either straight up or straight down, left, right. Otherwise, we have to start doing some funky math, right? I want to ask you, do we need both summation equations for this? We do need 2. We need to keep them separate, but do we need both to solve this question? Are you sure? What do we need? So what are we, take a step back, what are we trying to find? Force of friction. Are we given anything about the applied force in the horizontal direction? No. So So we don't have enough information to use the horizontal summation equation. And what did I say we were probably going to use at the very beginning? That force of friction equation. What do we need from the force of friction equation? The coefficient of friction, which we have, and the normal force. Where is the normal force? Is it in the y direction or the x direction? It's in the y direction. So for this one, we don't really need the x summation equation. If you want to write it, please don't skip steps unless you're sure you can skip steps. But I'm just pointing out hey, look, we can skip a step here, right? So for this one, all we need is the y summation equation because we need to know about the normal force. And we just have the normal force minus the force of gravity. What's our third step? Use Newton's second law. And Newton's second law tells us that the net force equals the object's mass times its acceleration. Is our object accelerating? How do we know? Say it again? I mean, it could be already moving and still accelerating, right? It could be already moving and still getting faster, or already moving and getting slower because of friction. What about the y direction? So like I said, we're going to skip the x direction because we don't really need it for this one. But what about in the y direction? Are we accelerating in the y direction, up and down? No, we're not. We're not falling into the floor. We're not launching this aluminum sculpture into the air. So we're not accelerating in the y direction. So what does that mean for the net force? Also, let me take a step back. So pretty much when we use Newton's second law, we're either going to plug in 0 or plug in mass times acceleration for the net force. In this case, if we're not accelerating, then we plug in 0, because if we have 0 acceleration, then we have 0 net force. What does that tell us for the net force and the force of gravity? They're equal to each other. Is that always the case? Is the net force always equal to the force of gravity? No, it's not, right? In an elevator, right, we had the issue with the elevator changing how moving would change the scale. So the scale showed us the normal force, and that changed, but our weight really hadn't. So normal force and force of gravity equals the force of gravity. This is not always true. And we'll see another example where it's not the case that the normal force equals the force of gravity. How does that help us? What do we need to do next? What do we need to do next? Huh? Kind of. We're almost there. Do we know what the normal force is yet? We know it's equal to the force of gravity, but do we know what the force of gravity is on this object? We need to find the force of gravity next, right? So we know that the normal force is equal to the force of gravity. So we need to figure out how much the force of gravity is pulling on this object. The mass of the object is 145 kilograms. We know that this is its mass because it's measured in kilograms. Times 9.81. I feel like that's not the right number. So this is 1,422.45. I like to keep all my decimals until the very end. So that's why you always see me write all my decimals. Now what? Now we can plug into this equation up here. Force of friction equals mu, the coefficient of friction. How much is the coefficient of friction in this situation? 0.47 times the normal force, which is equal to the force of gravity, so 1,422.45. So this is 669 newtons. And I'm not really picky about significant figures. I just say keep 3 digits. So like 669. 3 digits, we're good. What do y'all think of that? So in case you want to, let me see. So just in case you're watching this later and you want to try this one on your own, the answer for like I'll call it part B, is 490.5 newtons. I recommend going through the whole thing. Try to go through the whole thing. Like, don't just like cheat and be like, oh, I know where to plug in this number and that number and then do it that way. Because that may or may not help you on the test. Try to go through and solve it for yourself later. Okay. Y'all ready for the next one? So this one. A 50-kilogram desk initially at rest on a horizontal floor requires 365 newtons of horizontal force to set it in motion. Once it's in motion, a 327 Newton force keeps it moving at a constant speed. What is the coefficient of static friction between the desk and the floor? So now we're looking for the coefficient of static friction, and since we see the word coefficient of static friction, That should give us a hint again, just like for the last one. We know at some point we're going to have to use this equation, right? Because that's the only place where coefficient of friction shows up. But let's go through and let's do our steps. So first step, do what? Free body diagram. Is there going to be a lot of difference between this free body diagram and our previous free body diagram, do you think? Probably not. So first step, free body diagram. We know we have the force of gravity. It's on a horizontal floor, so that means the normal force goes straight up. There is a horizontal force pushing it. So we have an applied force. And then it mentions friction, so we can assume there's friction. What's our second step? The summation equations. And I am going to go ahead and do both summation equations for this one. So we have the y summation equation. So our vertical forces, we have the normal force minus the force of gravity. And in the x direction, we have the applied force minus the force of friction. What's our third step? Newton's second law. What is our object doing in the y direction? Nothing in the y direction. It's not exploding up off of the ground. It's not being falling into the floor. So what does that tell us about the net force in the y direction? It's equal to 0. What about in the x direction? So especially when it's talking about static friction, the situation that you should have in mind is you're pushing, 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 and it's not budging. So what's our acceleration in the x direction? Also 0, right? If it's not moving, it's not accelerating. And that means our net force is also 0. Okay, so let's take a step back. So like kind of the new like fourth step is take a step back and see what are you trying to solve. And look at the big picture. So what are we actually trying to solve for? We're trying to solve for the coefficient of friction. And the coefficient of friction is in this equation. It's right there. So that means we need to know about the quantity of the force of friction, the magnitude of the force of friction, and we need to know the magnitude of the normal force. Where do we find the force of friction? How can we find that? Which summation equation? the horizontal summation equation, right? So what do we know about the force of friction and the applied force? Huh? So the force of the applied force minus the force of friction equals 0. Yeah, so that means the applied force equals the force of friction. Do we know how much force we're applying? We're pushing, 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 and it's not budging? Or just barely starting to budge? This force. So we know that the force of friction is 365 newtons. Cool, we know that part. Now we need to know about the normal force. So what do we know? The normal force is in which summation equation? The x summation equation or the y summation equation? The y summation equation. And we know that the normal force minus the force of gravity is 0. So what does that tell us about the normal force and the force of gravity? They're also equal to each other. So that means we need to figure out what the force of gravity on this object is. The object's mass is 50 kilograms, and we're sure that it's its mass and not its weight, are we? How do we know it's the mass and not the weight? Because it has the units of kilograms. So 50 kilograms times 9.81 is 490.5 newtons. Why did we solve for the force of gravity again? What were we doing? Because it's equal to the normal force. And we need the normal force for this up here. Okay, cool. So we're almost done, huh? So I'm going to rewrite it over here. Force of friction equals mu times the normal force. The force of friction was 365. The normal force is 490.5. So mu is going to be 0.744. And mu doesn't have a unit. So it's just 0.744. If you go back and solve this one later, so if you're going back later and trying to solve for the coefficient of friction, your answer will be 0.667. So if you want to write that down, save it for later. What do y'all think so far? Where would you get stuck on any of these? What would be the step where you get stuck? The summation equations part? If you've got your free body diagram, then you're pretty much just looking at the free body diagram to get the summation equations, right? So like for the y summation equations, it's anything that's like pointed up. For the x summation equations, it's anything that's horizontal. Yeah. So the setting equal to 0 is the kind of the third step, right? If it's not accelerating, then the net force equals 0. If it is accelerating, then we need to know the mass and the acceleration, and we plug in mass and acceleration. What does constant speed mean for the acceleration? Those are some good questions. I can't remember off the top of my head. I mean, it might be moving at a constant speed. It might be accelerating, but like I said, it's kind of, I don't know if I have an example like that right now. I will check and see what's on the test. Okay, so next one. I want to show you some ones where we've got some forces at angles. Because sometimes you don't push something straight, like horizontally. You might be pulling on it, you might be pushing it down a little bit. And just like we had with our previous vectors, right triangles are really important. So if something is at an angle, if there's a force going at an angle, what you're going to do is you're going to figure out that x component and the y component. And when you need to calculate the components, you're going to use sine, cosine, or tangent. Most of the time when calculating the components, you'll use sine and cosine. Ready for an example? Or are y'all still jotting stuff down? I'm assuming y'all are ready. Okay, so here's our example. A 20 Newton box, and this one has kind of two parts. The first part, we're going to solve for the force of friction, and the next one, we solve for the coefficient of friction with the same information. And this one is kind of the easy part. A 20 Newton box is dragged on a carpeted floor with a rope at a constant speed. There is 6 newtons of tension in the rope, and the rope is held at a 30-degree angle with the floor. What is the magnitude of the force of friction between the box and the floor? So even though we've got some angles, we still do the same 3 steps to start off with. So first step, draw the free body diagram. So our free body diagram still has gravity, and gravity still pulls straight down. We're on a floor, so we have a surface that the box is supported from, and the floor is horizontal. We can kind of see that in the picture, which means the normal force is going to go straight up. It does mention a carpet. Carpets usually have a decent amount of friction. So we have the force of friction. But this time our applied force, or our force of tension, is at an angle. And we know that the angle is measured from the floor 30 degrees. When you see an angle like that, I think it would be good in your free body diagram to just go ahead and put force in the x direction, and in this case it's tension, and force of tension in the y direction. So I'm doing it in a different color because those are the components, they're not the force itself, right? So we don't have two extra, like, force of tension and some, like those are the components, right? That's what I'm trying to say. What's our second step? Summation equations, right? And it's still the same thing. We're going to have a summation equation for the y direction. And we're going to have a summation equation for the x direction. So what forces do we have in the y direction? Still have the normal force. We still have the force of gravity. Are those all the forces that we have in the y direction? We have the force of tension in the y direction. Is that a positive force or a negative force? Why is it positive? Because it's going up. Does it have to be positive, this thing? No, because we could, in theory, push down on something at an angle too, right? We could push something down, and that would be a negative applied force. But in this case, we're pulling up. What about in the x direction? Oops. Well, let me erase this. Hang on. It is a rope, so let me call it force of tension. I'm not picky, but I labeled it as force of tension in my free body diagram. If you want to call it force applied in the y direction and force applied in the x direction, that's perfectly fine. I did that for second period. I'm not so picky with those. I'm just rewriting this because I already had it written as force of tension in my free body diagram. So in the x direction, we have force of tension in the x direction. It has to be that component minus the force of friction. That's our second step. And then what's our third step again? Essentially, it boils down to, is the net force equal to 0, or is the net force equal to the mass and times the acceleration, right? If we're not accelerating, then it equals 0. If we are accelerating, then we're going to have to use mass and acceleration to get some extra information. In the y direction, is our box accelerating? Is it accelerating up or accelerating down? Is it exploding off of the floor? Getting launched off of the floor? No. So this, we know, is 0. I'm going to write it over here this time. What about in the x direction? It's being dragged across the floor, but are we accelerating it across the floor? What does it say? Constant speed. So that means in the x direction, we also have 0 acceleration. Okay, so that's our first 3 steps. Let's take a step back. So our new kind of 4th step is kind of like take a step back. What were we actually being asked to solve? What does it say? Force of friction. So we're trying to figure out what the force of friction is. Where do we find the force of friction? In the horizontal summation equation or the vertical summation equation? Horizontal? I know, I gotta ask the dumb questions so that y'all don't feel dumb. It's okay. I know, y'all are looking at me like, why do you keep asking these questions? Because I know somebody has them. And because the force of tension minus the force of friction equals 0, that means we know the force of tension in the x direction equals the force of friction, which is kind of awesome, because that means we're almost done. We don't have to solve for anything else. We're just going to have to solve for the force of tension in the x direction. So how do we solve for components of things in like x direction and y direction? Trig. Pretty much always trig. So, so we've kind of got a little picture of the little triangle over here. We are trying to figure out what this component is. Is that our adjacent side to the angle? By the way, in this one, the angle's there. Is that our adjacent side or our opposite side? That's the adjacent side. So we need to use a trig function with adjacent in it. So that narrows it down to cosine and tangent. And which of those sides do we already know about? We already know about either the hypotenuse or the opposite side. We know about the hypotenuse. How much is the hypotenuse? 6 newtons. So if we know about the hypotenuse, then in order to solve for the adjacent side, we need to use cosine. Now the best ways of writing the trig functions for physics look like this. Which is just slightly different than how you see it in math. Normally in math you see it cosine of the angle equals the adjacent divided by the hypotenuse. But most of the time in physics we're looking for one of the sides, either the opposite side or the adjacent side. And if we were looking for the opposite side, we would write this. So the adjacent side is the force of tension in the x direction. The hypotenuse is the force of tension itself times cosine of 30 degrees. Make sure that your calculator is in degree mode, especially if you've recently been in math class and you were using radians, especially if like you're taking pre-cal. You might be using radians more often. Make sure your calculator is the green mode for physics. So we would have 6 times cosine of 30, and the answer is 5.196 newtons. It's a force, so we know it has a unit of newtons. How did that help us? Are we done? What did we just find? We found the force of tension in the x direction, right? Why did we do that? Because it's the same as the force of friction. So are we done? Yeah. For this one? Yeah. We're done. Ta-da! 1, and we can round it. For our final answer, it would be like 20 newtons. Let me make that look nicer. 5.20. So what do you think for that one? It's the same 3 steps, right? So we start off with the same 3 steps. Draw the picture, write the summation equations, use mass and acceleration to figure out the net force. And then right now we're just adding a little bit more trig, right? And a little bit extra step to kind of figure our way to the very end. Now, like I said, the next question is pretty much the same, so I'll rewrite the stuff that we need. So it's the same situation, but now we need to find the coefficient of friction. So we found the force of friction before. And I'm going to write the whole number, because now that we're back into doing calculations, we should use the longer number. And now that it's asking us about the coefficient of friction, we also know that we're going to use this equation, right? We're looking for the coefficient of friction. We've already found the force of friction. So that means we need to figure out what the normal force is. And where do we find the normal force? In our y summation equation. So I'm going to rewrite that from the previous slide. So we had normal force minus the force of gravity, but plus the force of tension in the y direction because we were going up. And we know that all of this also from the previous slide, we know this equals 0. Okay. So, in order to solve our problem, we need to find the normal force. So can we move all of these things, the force of gravity and the force of tension in the y direction, to the other side of our equation? Yeah. So we can have normal force equals force of gravity now becomes positive because we moved it to the other side, and force of tension becomes negative. So I moved it to the other side and then I flipped it around too. Like I did a flip-flop. Okay, so force of gravity. Do we need to solve for the force of gravity? Are you sure? What do we know about this box? It's on the floor. It's not equal to the normal force, right? So in this situation, look at it here, right? The force of gravity does not equal the normal force. We've got a little extra bit. But that's okay. Do we know what the force of gravity is pulling on this object? Are you sure? Yeah. What's up with that? That's different than our previous problems. It's measured in newtons. This is telling us the force of gravity. Awesome. We don't have to solve for it. Yay! That's awesome. All right, what about, so we've got that. Can we solve for the force of tension in the y direction? Yeah, right? Just like we did solved for the force of tension in the x direction, but now this time the force of tension in the y direction, we'll use sine. So our opposite side equals the hypotenuse times sine of the angle. So in this case, the hypotenuse was how much? 6. Sine of 30, which is 3. So over here we have 20 minus 3. So our normal force is 17 newtons. But do you see, like that can make a big difference in your calculations and whether you get the question right or wrong. And it can also make it really simple sometimes, depending on what we've given you. So over here, we did, I skipped a couple steps. So we did, like, add the force of gravity to both sides and subtract the force of tension in the y direction? Is that what you're asking? Okay. So we would have force of gravity minus the force of tension in the y direction equals the normal force, and then I flip-flopped it. A plus B equals B plus A, or like, no. Yes. No, if A equals C, then C equals A. Flip-flopped. All right, almost done. So, up here, what was our force of friction? I've got to check by it. That means we've got it somewhere. It's what we calculated before on the previous problem, right? So this is 5.196. The normal force is what we solved for down here, so 17. So this is 0.305. And again, mu has no units, so just that. Does this also fit with one of the things we know about the coefficient of friction? Coefficient of friction should always be less than 1. Yep, so we know we did it more or less correctly. There is another one. So there is an example of the box being pushed down. I'll make sure that I have this solved out for y'all as well, probably in a separate video, so that you can try it on your own as well.